Four talks, and the first will be given by Adam Klivans from UT Austin. And it will be about efficient algorithms for outlier-robust regression.
Thank you. Wow, this is on. It's supposed to be on like that? Oh, okay. Thanks to Ilias and the rest of the organizers for inviting me to the workshop. It's a great workshop. Thank you, Ilias. Continuing on the theme of talks from this morning, I'm going to talk about efficient algorithms for a supervised learning problem. This one, maybe the most basic of supervised learning problems, just ordinary regression. And I should say this is joint work with Pravesh Kothari, who'll be joining CMU, and Raghu Mecca, who's a professor at UCLA. So as I was saying, your sort of most basic supervised learning problem, ordinary least squares regression. You have a set of data points. You want to find the best fitting line with respect to square loss. And there are various models that we could consider for this problem. One is what I would call the realizable model, where your values y are actually some linear function of your covariates x. There's another model called the probabilistic concept model, where you assume that the conditional mean function is actually some linear function of w inner product x. And typically, throughout the talk, I'll write L star when I want to refer to the best fitting line with respect to square loss in this scenario. So we're going to consider a problem that's just a little bit more difficult. I'm going to work in what I would call the agnostic model of learning. And here the setup is that we have some joint distribution D on R to the D cross 0, 1. So I'm going to assume that all of your labels are coming from some bounded set 0, 1. And then because the scenario is not realizable, I'm going to define this quantity called opt, which is the error, the square loss error, for the best fitting linear function, w. And then we're going to be given draws s from some training set. And I just want to, and what is your goal? Your goal is to output some, so let's see if my writing works. So you want to oh no. So you want to output some L such that the square loss of L is something like opt plus epsilon. So you know the error of the best fitting linear function is opt. You want to output some other linear function whose square loss is very close to opt. And what you're given are draws, IID draws from this distribution D. And as many of you know, this problem is actually solvable in polynomial time by first applying any efficient algorithm for least squares regression. You could run gradient descent over your sample. You could compute the SVD, whatever you'd like to do. And then applying an appropriate generalization bound. Because what we really want to do is come up with a linear function whose square loss with respect to future draws from the distribution is within epsilon of optimal. Yeah.
That's a quick question. So gradient descent works here?
Sure.
Very noise with condition number, nothing, that's fine?
Yeah, it's fine. Yeah. Yeah.
So it's quadratic function, yeah.
So I'm sorry to go over this, super basic problem, but actually as an anecdote, Ravi Kannan is speaking after me, and I remember when I took his undergraduate automata theory class, I think I was a senior at the time. Do I have time to tell this anecdote?
No.
Okay, so when I was a senior at the time at Carnegie Mellon, we had all taken algorithms, and actually a bunch of us had taken, graduate computational complexity. We were very ambitious and sort of naive undergrads. And so then we took Ravi's course, which was an undergrad course in automata theory, and he lectured to us about NP completeness, and I remember he started just defining NP completeness and reductions, and I think someone sitting next to me was like, yeah, we've seen all this before. And then As if on cue, Ravi was like, I know you've probably seen this before, but it's never bad to see things like twice. And then it actually occurred to me while I was doing it that like I really didn't understand enemy completeness, and that I actually needed to see it another time. So this is not to say that you don't understand ordinary least squares regression, only to say that I don't feel bad about defining it again.
Question actually about this claim. Is this solvable? I mean, what if like D has some with very low probability, some vector where X is gigantic?
Yeah, I'm bounding everything.
Okay, so this is not really...
Actually, you don't need to worry about X being gigantic. You need to worry about the label being gigantic.
Well, if X is gigantic, then you might be forced to... The opt will be a W that's perpendicular to that gigantic X or something.
I'm also bounding like, the domain of the optimal weight vector.
That's not affecting anything, I don't think.
You're saying the L2 norm of W?
Like, I mean, just if there's some low probability of there being a tremendously large X, then even if W has absolute value 1, it had better be almost orthogonal to that X.
Depends on the Y. That corresponds to that X.
What?
It depends on the Y that corresponds to that X.
Yeah, it depends on the Y.
Between 0 and 1.
Yeah.
It depends the kind of generalization you want. If you are happy with dimension dependent, then as long as the domain with respect to which
is bounded, then it's not a problem.
Well, fine. Yeah, if you're willing to replace R to the D by 0, 1 to the D or something, that's fine.
Actually, you need something weaker than that. For example, if I can bound like the covariance of...
Fine. Or you can bound the covariance of X or something like that.
Think of everything as bound... Well... Yeah. Okay. So the setup here, still going with the setup is... So now I'm going to introduce noise to the problem. So my training set S is M draws x1, y1, x2, y2, xm, ym, and each xi, yi set is in 0, 1. So now I'm going to allow an adversary to come and corrupt an eta fraction of the points in S, however he, she wants. And I'm going to call this corrupted set U. And all that I'm going to require is that the size of U intersect S divided by the size of S is at least 1 minus eta. Okay, so the adversary can actually corrupt an eta fraction of points however he wants. And this is more general than, say, the Huber contamination model. And the dream result would be that even given samples that have been corrupted, I'm still able to output a linear function L that has error approximately opt plus epsilon with respect to the distribution from which these samples were drawn. Okay, so is the dream result is clear? Okay. We're going to do something like this. We are going to give, so there's been some contemporaneous work that I'll mention on the next slide. But as far as I could tell, or we were aware, there were actually no results along these lines. So we sort of give the first efficient algorithms for solving this problem. We're not going to get opt plus epsilon. We'll get something sort of like opt plus epsilon. We also prove that in general, if you don't take an assumption on the marginal distribution on X, that it's impossible to get this dream result. It's impossible to solve this problem. And like I said, even, as far as we were aware, even exponential time algorithms that satisfied these properties weren't known. Okay, so informally, what do we actually do? We come up with a polynomial time algorithm that will output some linear function L. And the square loss of L, remember we wanted opt plus epsilon. Instead, we're going to get 1 plus order square root eta times opt, plus order square root of eta times this term right here, which is slightly annoying. But you can actually improve this bound and put an L star there. So at least in the case where you have a realizable model, or even when the conditional mean function is equal to L star inner product X, this term will go to 0. And this term, opt, will be 0. And you'll actually be able to recover the original linear function. Okay, but for kind of simpler models where you assume, say, realizability, we'll actually be able to recover. We'll sort of get the dream result that we wanted. And for these more general models, the agnostic setting, we'll get something like opt plus epsilon with these factors 1 plus square root of eta sitting there. And we'll also need as I mentioned, assumptions on the distribution on the marginal distribution on X. But as I mentioned, these assumptions are unavoidable because if you don't take one, the problem is impossible. Okay. And I guess I also want to mention there's been a lot of independent concurrent work on this problem. There's a paper by Diakonikoulos, Kong, and Stewart. They considered the case when X is a spherical Gaussian. Is that right, Elias? When the marginal distribution on X is the Gaussian?
Also for general, but let's say Gaussian.
Okay, for Gaussian. And then there's this Diakonikoulos, Kamath, Kane, Lee, Stewart, Steinhardt paper that contains this Sever algorithm that also will sort of solve this problem. And there was some work by some people at CMU, Prasad, Sugala, Balakrishnan, and Ravi Kumar. Let me just point out what distinguishes the results in this paper from these contemporaneous works. And that is that what we were concerned about was sort of this agnostic setting where I don't assume that anything's realizable. And we wanted to put as few assumptions as possible on the distribution. So I think that our results are sort of the most general. They don't get the sharpest bounds. And we're also going to use a different set of techniques, some of which were described by Jerry in the morning talk, sum of squares, and I'll talk about that in a little bit. Yes?
So under your assumptions about the marginals, even if opt is 0, do you know if this root eta is information theoretically the best thing you can do there?
Yes, I do, and it is. Yes, so we have examples. I'll talk about it later in the talk. Okay. Okay, so forget about computation for a second. Here's a naive strategy that you might employ to try and solve this problem. Okay, so again, S is the original training set that you get, and S prime is the corrupted training set. Okay, so remember I said even a brute force search algorithm wasn't known. So why not try brute force search? Literally take all possible subsets of size 1 minus eta times the size of S, and then for each one of those subsets, use ordinary least squares for that subset to come up with some linear function, and output that W, that linear function that you get that has the minimal square loss over all of these subsets. Okay. One nice thing about this strategy is that certainly one of the subsets that you try will be the truly uncorrupted subset. So one of the linear functions that you get is actually going to be the optimal linear function. But the problem is that an adversary could make your set strange in such a way that you actually find some other linear function whose square loss is even smaller on this corrupted training set, but it doesn't generalize well with respect to the original distribution. So you end up taking the smallest one with minimal square loss, and then you fail. Okay, so that's really the problem with this algorithm. Nevertheless, you can actually prove that this will succeed if you assume something about the marginal distribution. For example, if you assume it's Gaussian, then this strategy will work. And what we're going to assume is that the marginal distribution is hypercontractive. Jerry also alluded to these distributions in the morning. He called them, I think bounded. Where are you, Jerry? What did you call them? Bounded?
Explicitly bounded.
Explicitly bounded. OK. And as he mentioned, they capture a lot of interesting distributions. For example, log concave distributions, all product distributions, Gaussians, non-spherical Gaussians even, which is kind of interesting. And so what we prove is basically the following simple structural lemma, and is that if you have two distributions, D1 and D2, and their total variation distance is bounded by eta, and then imagine that D2 is uniform on S prime, okay, your corrupted set, and imagine that D1 is uniform on S, your uncorrupted set. So we prove this inequality. What is this inequality saying? Well, you find some W prime, let's say via brute force search or whatnot, that has small square loss with respect to D2. Okay, that's the one you found from brute force search. This inequality says, actually, that linear function that you found, really, it's not doing so bad with respect to the uncorrupted distribution, D1, the uniform on the samples that were uncorrupted either. If that's the case, then I'm in good shape because I can apply some sort of generalization bound for W prime that I find, and I'll know that it's good with respect to the original true distribution that I was looking for. And one nice thing about this little lemma that we prove is that the proof is simple enough to be encoded into something called a sum of squares proof system. Questions about the statement of this lemma?
So we have the dots.
Oh, yeah, that was that. I had that fourth power of L inner product X, so that's basically the dot, dot, dot. Okay, so I want to prove this to you. And as I said, think of D1 as uniform on the uncorrupted set. D2 is uniform on the corrupted set. We have our bound on the total variation distance. And now I'm going to slightly change the game on you a little bit. Instead of square loss, I'm going to look at absolute loss. I'm going to prove the lemma for you for absolute loss because the proof is even easier than square loss. And when I do this, I also need a bound on the condition number of D1. So that's kappa, so that's the condition number of the true covariance matrix for D1. For square loss, I don't need this bound kappa, but for absolute loss, you do need this bound kappa. But I wanted to prove it to you for absolute loss. Okay, and so remember, I want to just relate the error of D2 of L to the error of D1 of L. Okay. Okay, so the proof starts off like this. Since the total variation distance of D1 and D2 is at most eta, then I know that there's a coupling G on this joint distribution x, y cross x prime, y prime. So x, y, these are drawn, you can think of these as being drawn from D1, and x prime, y prime, they're being drawn from D2. And the coupling, if you're familiar with this, has the following nice properties. The marginal, so G is a distribution, and its marginal on xy is actually equal to D1. Its marginal on x prime, y prime is equal to D2. And the probability when I sample from G that I get xy that's not equal to x prime, y prime, that's at most eta. Okay, so I've seen total variation distance defined this way, so there's nothing deep going on here. But we need this coupling. This is how we're going to relate the error from D1 to D2. Okay. Okay, so now I want to show you, this lemma, this robust certifiability lemma. Who wants to see me prove it, like in real time, on my iPad? Okay, everyone wants to see me prove it. Okay, good. All right, let me make sure I have the right pen. Okay, yeah, right. So we have TV, D1 and D2 is at most eta. That's good. Okay, so what do I want? I want to understand expectation with respect to D1 of y minus L inner product x, the absolute loss. Okay, this is what I want to bound, but I want to bound it in terms of something with respect to D2. So my first move here is going to be to use the coupling. Okay, so this is the expectation of the indicator function xy equals x prime y prime times the absolute value of y Lx. Okay, and then the other case is that xy does not equal x prime y prime times y minus Lx. Okay. So far, I think this is pretty good. Now, so I haven't screwed it up yet. So I have these two terms. Okay, let's look at the first term. I want to claim that the first term is less than or equal to the expectation with respect to D2 now. So this is D2 of y minus L inner product x. Why is that? Well, in this first term, xy equals x prime y prime. So, you know, when I have a d2 here, I have x prime y prime. And there are some terms that won't contribute to this absolute loss. Those are the ones where xy does not equal x prime y prime, and that's why I have an inequality. Okay, so this first term really is just the error with respect to d2. There we've shifted to the error with respect to d2. Did that make sense? Okay, good. Now I have this other term, and I'm going to apply Cauchy-Schwarz. So I'm going to get square root of expectation of g, 1, xy not equal to x prime y prime squared times square root, whoops, square root expectation of d1 y minus L inner product x quantity squared. Okay, why did we get to move to d1? Well, x and y, you know, those are the variables that are drawn from d1. So instead of g, I'm only concerned with withdrawals from d1. And this square here, so this term in here is eta because that was the fraction of points that the adversary corrupted. I mean, that's the statistical. I mean, that's the total variation distance. So I get a square root of eta. And then this term, expectation of y minus Lx squared, I can just bound this by twice the expectation of y squared plus twice the expectation of Lx squared. And then remember, L star was my optimal linear function, and we said the norm of L was smaller than the norm of L star. So this term is at most 2 times kappa times expectation d1 L star x squared. Okay, so we're done. We did it. You know, here's the left-hand side. This is what we wanted to bound. We said that the error with respect to the uncorrupted distribution is at most the error with respect to the corrupted distribution plus square root of eta. And the square root of eta gets multiplied by 2 expectation of y squared and 2 kappa expectation from d. This is sort of like your opt. This is like 2 kappa times opt with respect to square loss. Okay?
What is kappa?
Kappa was the condition number of the covariance matrix for the original distribution. Okay, so I have L inner product x here, and that's at most L star times kappa, because the norm of L is at most the norm of L star. Okay, so we called this a robust certifiability lemma. 2 things to note were that the only real inequality that we used here was the Cauchy-Schwarz inequality. And also, you see that you have sort of squares of linear forms. You might want to remember that basically there's nothing more than comparisons of relatively low degree polynomials going on here in these inequalities. Okay. Questions about this robust? Yes?
So you did not use hypercontractivity?
Not yet, no. So interestingly, for the absolute loss case, I don't need to use hypercontractivity, but I do need to depend on this condition number of the distribution.
Of course, no fourth moment appears here, right?
There's no fourth moment here, right.
So
I could use 1-2 hypercontractivity if I wanted. Right. Okay, so for square loss, if you want to see what happens for square loss, then I need to assume that instead of a condition number on D1, I'm going to assume that it's hypercontractive. That's a fancy way of saying that I can bound its fourth moment in terms of some constant times its second moment squared. Okay, and the actual statement that you get will be similar to the one that we got for the absolute loss. This time I'm going to bound the square loss. And there's that square root of eta coming in again. I have a hypercontractivity constant. This is my opt. And then I get, again, the hypercontractivity constant, square root of eta, and this sort of annoying fourth power sitting there. And you can see if you wanted to prove it for square loss, you would use the same approach for absolute loss. But so we would do the same thing that we did here. But instead of a square root of expectation of y minus L of x squared, if we're starting with square loss, you end up with a 4 here. So then I have fourth moments. And so then I need to bound everything using hypercontractivity in terms of the second moments. Okay, so that's why absolute loss was nice. I didn't need to go to the fourth moment. If you want robust certifiability, if you want the same lemma for L2 for square loss, then I do need to worry about fourth moments, and so I have to use these hypercontractive inequalities. And one thing to point out is, and I don't want to hide this, is that we do need, if you look through the proof, you do need that 2 times the hypercontractivity constant times square root of eta is at most 1. So you need this sort of technical condition on eta. Remember, eta is the amount of noise that an adversary is allowed to corrupt. And when the distribution is Gaussian, it turns out that eta is something like 0.29. Okay, so as long as the fraction of errors that the adversary corrupts is less than like a quarter, there'll be no problems with this proof. But depending on what the marginal distribution is for D1, you may have different tolerances for different parameters of eta. Okay. So this basically tells us that this proves to you that the brute force search algorithm works as long as you make these assumptions on the marginal distribution for D1. Now we want to come up with a polynomial time algorithm. How are we going to do that? Much the same way that Jerry did it in his talk. We're going to appeal to the sum of squares proof system and do a non-convex relaxation to find the subset that we're looking for. So let me try and show you how this works without resorting to Marley's theorem. Okay, I'll say as much as I can. Okay. So let me actually show you what the non-convex program is, and then you could imagine how you would relax it. Okay, so what's the non-convex program? So it's a system of polynomial inequalities. So remember that, just to set this up, ui and vi, those are going to be our corrupted points. And then our non-convex program is going to have the following variables. It's going to have w. The w's are going to be used to select that subset. Remember when we were brute force searching through subsets, now we don't want to do brute force search anymore, but we somehow want to select a good subset. L is a set of variables corresponding to the linear function that we're looking for. And then we're actually going to have these other variables, xi prime, yi primes. Those are again enforcing that we're actually choosing elements from our corrupted set. Okay, so yeah.
So W is an array actually.
RD.
But doesn't it?
Oh, sorry, you're right. Sorry, thank you. Yeah. So the objective function is going to be 1 over n. This is what we're trying to minimize. Okay, and then I'm going to have the following constraints. The sum of the wi's is going to be at least 1 minus eta times n. So the weights are going to select the points, so they should be at least of 1 minus eta times n. Then I'm going to have wi squared equals wi. Wi times ui minus xi prime should equal 0. Wi times ui minus yi. So every time, so wi squared equals wi enforces that wi is either 0 or 1. And every time that wi is 1, it means that you're selecting ui. Every time wi is 1 for one of these xi prime constraints, you're selecting a ui. And every time that wi is 1 for one of these vi constraints, it means these yi prime constraints, it means you're selecting a vi. Okay, so we could write this program. If we're still not interested in polynomial time, we could solve the program. We could come up with a linear function, a set of weights, a set of points from our corrupted set, and that would correspond precisely to a subset that we're searching for. And furthermore, the subset that we're searching for is large. So the uniform distribution over that subset is going to have small variation distance with respect to the uniform distribution on the original corrupted set. And so we can apply one of those robust certifiability lemmas. OK? Good. This is the program. OK, so now I'm going to make the problem even harder. Instead of actually searching for a linear function, I'm going to search for a distribution over feasible solutions to this non-convex program. So for example, so this is a harder problem because I could find some distribution whose support is only on the feasible points of that original non-convex program. But I'm just going to I'm going to demand that we find some distribution on them. Okay, and I'm going to demand furthermore that if you sample a solution from this distribution mu, this quantity, the objective function, is minimized. Okay, so our constraints are going to be satisfied, and we're going to minimize our objective. So this problem is even harder. So there's no polynomial time algorithm to do it. But instead, if you look at a relaxation of this program, and this is part of the sum of squares methodology, instead of you actually can compute something called a pseudo distribution. It's not a real distribution on feasible points on your non-convex program. It's something else. Okay? And it has the following properties. So what properties does a pseudo distribution have? Well, like a normal probability distribution, it sums to 1. Okay, good. And the sum of this distribution times f of x squared for any low degree polynomial f must be greater than 0. And if this is so, more technically, if it's the case that your pseudo distribution is positive times any polynomial f of degree L over 2, then we say that D is a level L pseudo distribution. And this pseudo distribution can actually be computed in time n to the order L. Okay, so one thing to notice is that if I took L to be infinity, then all of my elements d of x would be positive, and it really would be a probability distribution. But it's not. I'm getting some relaxed version of a probability distribution. OK, so to summarize, what does this mean? So instead of solving for L, W, xi prime, and yi prime, instead I'm going to compute their pseudo expectations. So I wanted to compute their expectations. Instead, I'm computing their pseudo expectations, which I'm denoting e twiddle mu twiddle of L. And one thing to note is that this value is actually a vector in R to the D. Okay, when I compute these pseudo expectations of level L, not only can I get the first moment, second moment, and so on and so forth, I can get the nth moment, pseudo moment of all of these variables. Here, all I'm going to need is the first moment, the first pseudo moment of this variable L. This is a vector in R to the D, and this is actually going to be, this is my solution that I'm going to output. Okay, so the linear function, the polynomial time algorithm is going to compute this pseudo expectation and then output this pseudo expectation with respect to mu twiddle of L. That's going to be my linear function that I actually output. Okay, that's going to be the algorithm. Any questions on this before I keep diving into the analysis? Okay. So my crude summary about pseudo expectations is that in all ways they behave like real expectations with respect to any inequalities that involve low degree polynomials. Okay, so if you have an inequality that involves degree 3 polynomials and you've computed a level 4 pseudo distribution, it sort of will plug right into those. It will fool those polynomial inequalities. The polynomial inequalities won't know the difference between true optimal solutions, true feasible distributions, and pseudo distributions. It's unable to distinguish them. Yeah. I have 5 more minutes. Okay. So let me just show you how we actually apply this in our context. Yeah.
Is that a rigorous statement?
I'm going to make it more rigorous in just a second.
That's cool.
It's fairly rigorous. It's as rigorous as Marley's theorem. It's slightly more rigorous than Marley's theorem. Okay. So I just have one slide on how we actually apply this. So remember that I'm calling opt-SOS. That was the minimum value. That was the optimal value of that objective when we took the STP relaxation. And it's definitely, the error of opt-SOS is definitely less than or equal to the opt of the best fitting linear function, because the best fitting linear function is a feasible solution to that program. And then I'm calling opt for this annoying fourth moment term. And what we know, what we proved, you remember when I excitingly proved the robust certifiability for square loss or absolute loss, what we actually proved was this inequality. But as you can see, this inequality, as we mentioned, only involves degree 4 polynomials. Okay, in fact, it involved applying a Cauchy-Schwarz inequality. And so some degree 2 or some degree 4 polynomials popped up. But that's essentially all that really happened. Okay, so by my crude understanding of pseudo expectations that I mentioned on the previous slide, if instead of, remember we proved this for linear functions, turns out you can also prove it for pseudo distributions. Okay, so instead of L here, I can get expectation, sorry. Error d1 of L on the left-hand side. And then on the right-hand side, when I plug in my pseudo expectation, I'll get opt-SOS here. And this stays as opt-for. And now I can apply convexity. And I'll get that error with respect to d1. I'll push this pseudo expectation inside, is at most this plus this. But remember, as I mentioned, this is actually a vector. So it's a linear function. So what we showed is that the error with respect to d1 of this pseudo expectation for L is actually at most this factor times opt-SOS plus the opt sub 4 here. Okay, so this is actually how we can relate the pseudo expectation to the optimal error from the original distribution. Okay, so it's plugging in the pseudo expectation and using convexity. Okay, so just to summarize, we don't solve the non-convex program. We only get a pseudo distribution on the solutions, but these pseudo expectations obey our inequalities. And so by applying convexity, we can argue, using that certifiability lemma, that this quantity is indeed the linear function that we're looking for. Okay, so just a couple of extensions. Everything that I've said, also works for higher degree polynomial regression, although now you have to use some tools on hypercontractivity of polynomials with respect to these distributions. It works for all certifiably hypercontractive distributions. And in the paper, we have an application for learning Boolean functions, which is a problem I'm very interested in. With respect to this nasty noise model, Ilias and Daniel and Alistair have a recent paper on this. But I put a question mark here because we need the error rate eta to be so small for our results on nasty noise with respect to Boolean functions that I'm not sure they really capture interesting classes of Boolean function learning. So I think it would be interesting to extend this type of work for Boolean functions. So I think I'll stop here.
Questions?
So another measure of error for these regression things is not how much I'm supposed to opt, but how much I differ in expectation from the prediction of the optimal estimator, L inner product, or L of x minus L star of x L norm squared.
Sure. Yeah.
Anything for that? Because that's a smaller value difference, right?
There you'll need to start assuming things about the
Yes.
condition number of the covariance matrix.
I see. Can you get like sublinear-ish working rates for that?
Sublinear?
Well, as in like, that error is usually like the quantity you have, like the op that you have is going to be roughly like n-ish, right? It's going to scale as you take more samples. And you got like average error which is decreasing beyond constant.
I don't know. I don't know. That's an interesting question.
Other questions?
So regarding the sort of exponential time algorithms, so there were some notions in the literature of like regression depth, like a generalization of the two-key depth to regression. But these might have been sort of precursors that are like robust and exponential time. Because maybe no one worked them out for S general distribution, but certainly for the Gaussian, etc. I think Chow has results. These are just information theoretic.
Oh, okay. Thanks, I didn't know that.
Other questions? Okay, if not, we can